Hello, AP Calculus AB students. Mr. Record here. Going to take a look at our first few examples from topic 6.3. I want to warn you a little bit. 6.3 is a pretty long topic. It starts pretty light, but it does get into some pretty complex stuff, especially from an algebraic standpoint. So I want to warn you ahead of time, by the time you get into examples 7 and 8, things are going to be a little challenging. However, if you gradually work through the videos and make sure that you understand everything or work through the content that we talk about in class, ask questions when you need to, you should be ready for the very end of this topic. So let's take a look and see what we've got with this review of summation notation. Not a lot of the things that we're going to do in this video is really going to pertain to calculus. This is going to be a review from some things that you may have learned in a previous course. But we do have this idea of the summation. In other words, if you have a series of values that you want to add together, there's a very short way to write that. And let's say that a sub 1 represents that expression. It's an expression that has the variable I in it, and you're going to let that I change from 1 to 2 to 3 to 4, all the way up to this upper bound, which for this particular general example I'll call n. Then all you do is you write those various results, the a sub 1, the a sub 2, the a sub 3, and you'll add them all together until you get to the very end, which is a sub n. This is a very, very important concept to really wrap up and become very comfortable with before you get to the end of, say, a Calculus BC course or a Calculus 2 course. Those particular courses end with this idea called series, and that's exactly what this produces. So let's take a look at example 1 and see if we can make a little bit better understanding of this. It says find the summation from I going from 1 to 6 of the value 1. Well, essentially what this says to do is to replace the I in this expression with 1, which is a very easy replacement. And then the summation symbol says you are going to add, and then we let I go to the next integer, 2, and then the summation says you are going to add, and then we let I be 3, followed by 4, followed by 5, all the way to 6. Good thing we didn't have to go much farther than that, huh? And by the time you add all of these numbers together, I'm going to assume that you guys could probably handle that. The answer is 21. Now, obviously, the larger this upper bound becomes, the more tedious it would get to write all these out. So we may talk about a simplified approach to this here in just a moment. Now, if you take a look at part B, the summation of j squared as j goes from 3 to 12. Well, again, if we choose to write these out, it's going to be a bit tedious because we replace the j with 3, and then of course any other operation around that j has to retain and act upon that 3. And then the summation says add, and then we let j be 4, and then we let j be 5. Well, you guys, I really don't feel like I want to write all of these all the way up to 12. So we know what's happening is eventually we get to that 12 squared. Well, I just don't have the heart to have you figure this out by hand because that's going to get to be a little bit ridiculous. So as you can see, this problem has a calculator icon next to it. So I just want to introduce how you would do this with your graphing calculator. So I'm going to switch over to my graphing calculator software, move my picture down here, and show you how to do this on the TI Inspire. Those of you watching using a TI-84, things are a little bit different. You have a setting called sum sequence that you need to move into to make sure that you're doing the same thing that we're about to do here with the Inspire. So you would hit this button next to the number 9. That's probably the quickest way to access this math template. And right about here in the middle of that second row, you see a nice summation symbol. When you hit enter, it basically is pretty self-explanatory. Fill in the missing fields with what you need to use for this problem to replicate it. J is going to run from 3 to 12. You're going to square J. And like I said before, the calculator is going to do all the work for you. You can't beat that. So you get 645. Now, if this problem is a non-calculator, there are ways that you can still do it fairly effortlessly, or at least without the mundane, idea of having to add all these, and we're going to talk about those a bit later. All right, now let's build the idea of summation properties and formulas, because we're going to be working with summations in an algebra environment, so we want to be able to perform operations on them. So one of our first properties is that if you have a constant that's kind of multiplying by your ith expression, your ith term expression, a sub I, you can in large part basically bring it out to the front, ignore it for a while, work with your summation, and then the k can multiply back in later. That's called the scalar multiple property. In short, bring your constants in front of the summation. And then properties 2 and 3, I'd like to talk about these two simultaneously because they're just the addition and summation properties. Now, the assumption here is that the A1 and B1 are both inside of the summation. And honestly, I probably should put parentheses around those to make sure that that is understood. A lot of times we kind of uh, take it for granted that that is the case, but they were to be both acted upon by the summation, and basically you're just allowed to split this into two separate summations, whether it was an addition problem or if it's a subtraction problem. There's your sum and difference properties. And then in the blue box, you have what I like to refer to as summation formulas. And these formulas are going to be very useful if you have to work with problems with large upper bounds and you don't get to use your calculator. It is not imperative that you memorize these summation formulas for the advanced placement calculus exam. So the formulas basically say if you add a constant and you let that constant summation run from 1 to n, you're just going to take that constant and multiply by n. This really makes a lot of sense when you think about writing it out in longhand, because you let your I be 1 and it really doesn't change what C is. You let your I be 2, it doesn't really change what C is. And you keep doing this over and over again until you put n number of C's down. And when you add n numbers of C, you get C times n. Now, 2, 3, and 4 are a little bit tougher to prove, and I'm not going to do that in this video because it's very much beyond the scope of the course. You would use an idea of inductive reasoning to prove each of these, which is typically taught in a more advanced version of a pre-calc course. But if you see a summation of just the letter I by itself, n times n plus 1 divided by 2 is the formula that will work. If you go back to the original first problem that we did, remember the summation as I goes from 1 to 6. Well, if I use this formula and let the n be 6, you get 6 times 7, all divided by 2, and lo and behold, 42 divided by 2 is 21, and that's exactly what we had here. So it's a really wonderful way to get your answers a bit faster. Now the summations for I squared, a little bit more complicated. It's got a little bit more going on with it, but again, you can just simply plug in that upper boundary and it will compute the result. Likewise, you have one final summation that's been proven and used all throughout the history of mathematics, and that's the summation of I to the third power. And again, if you just take that upper boundary and plug in for the n value, you'll get this result. Now note, all of these formulas only work if the lower boundary is a 1. So that means if we were going to do our example B, we'd have to be a little bit more clever. And I think I have an example or an exercise in the skill builder that will use that idea that I want you to think through. Little historical note here. Carl Friedrich Gauss, a German mathematician, was a mathematical prodigy at a very young age, and he's renowned for stumbling upon the summation formula number 2 at the age of 5. Now, sometimes people think that this is a bit of a tall tale, but I'm going to give you the quick 1-minute version of this story. When this particular mathematician was a young lad in kindergarten, he had a very difficult time being challenged because everyone knew at that point that he was pretty gifted mathematically. And I guess the story goes one day that he was sitting in class, and back in that time, they had inkwells on their desk, and the girl sitting in front of him had this beautiful blonde hair, the little Fraulein, and he accidentally took her pigtail and dipped it into the inkwell. Of course, the teacher's not happy. He gets in trouble. He makes them stay after class during recess, and his punishment is to add the numbers from 1 to 100. Well, the normal kindergartner probably can't do that, but Carl Friedrich Gauss actually was able to come up with that answer much faster than the teacher had ever anticipated. And his approach was quite interesting because the story goes that he said, well, I'm just going to add all of the numbers from 1 to 100. By golly. Well, how about we do that both forwards and backwards? Well, that's kind of unusual. Why would he think to do it this way? Well, he noticed that when he adds these numbers together in their respective columns, that he simply gets 101 each time. And in fact, he gets 101 a total of 100 times. However, this is the result of adding 1 to 100 once and twice. So how about we divide that by 2? And lo and behold, he was able to do this work. I think you get 5,050. And when you look at this statement, it very much looks like this property. And the kid was 5. Now, please understand, he did not discover this formula. It had been discovered long before, but it was interesting how he stumbled upon it at such an early age. Let's go ahead and take a look at another example here. Number 2, evaluate the following summation. Now, this is what I talked about here a moment ago. The summation runs from 1 to 10, which is kind of in that zone where do we really want to plug in the numbers and figure out what this is, or maybe we want to rely on those wonderful formulas or those properties that we just saw. So if we do that, we first know that we are indeed allowed to break this apart into 3 separate summations. So we'll have the summation of I squared from 1 to 10 minus the summation of I as I goes from 1 to 10. And then we would add the summation of 4 as I goes from 1 to 10. Now what that's going to do is it's going to invoke our properties. The I squared property, now you have it in your notes. You might have to flip back a page. If you're watching the video here without the notes packet, right here is that I squared formula that I need. So we're going to run that in here, and we get n times n plus 1 times 2n plus 1, all divided by 6. That's that first formula. And then the subtraction drops. The summation formula for I, that's the one that our little Carl Friedrich Gauss stumbled upon at the age of 5, and it looks like this. And then for the summation of 4, if you remember, that answer is just C times N, where C is 4, so you have 4 times N. And I note that all of these have the same upper boundary of 10. They all have the lower boundary of 1. Thank goodness. So that means that we can evaluate this such that N is equal to 10. So I guess you can just plug 10 in for all of these values of N, and you come up with 10 times 11 plus, or times 21, all over 6, minus 10 times 11 all over 2, plus 4 times 10, which is 40. And at this point, you could either reach for a calculator perhaps, but if you're using your TI Inspire or a TI-84, you could have done this from the very get-go. So it's likely that this is not a calculator problem. So you have to kind of bite the bullet, do a little bit of simplifying here. It's not as bad as you think, I promise, because you could do some canceling. 6 and 21 would be 7 with a taken out a 3, and then 2 and 10 reduce as such. So you have 5 times 11 times 7 right here. And then, of course, 10 over 2 is 5, times 11 is 55. So basically, if you can get to a point where you can multiply 35 times 11, you're in good shape. Well, I have a trick. Whenever you multiply numbers by 11, it's actually quite easy because you just take the first digit in the first spot, the second digit in the last spot, and add the 2 digits together, and that's the middle value. I promise it works every time. Check it out. So you have 385 plus 40 plus 55, which means, oops, I take that back. This 55 has a subtraction. Apologize for that. So you have 385 minus 55, which is 330. Add 40, and then you get 370. Okay. Now let's finish up by looking at example 3, which is a little bit different type of problem. You're kind of working backwards, so to speak. This time I'm giving you a series of terms, let's say, and you are supposed to identify what would the summation notation look like that matches this particular sigma or series notation. So we write our summation, our sigma. You're going to write this quite a bit in your careers in mathematics from here on out, so you want to get kind of used to it. And then what I typically tell students to do is look throughout the problem and replicate what's constant. What do you see always as you move from one term to the next term to the next term? Well, there's a lot of things that you see that are the same, like a fraction. There's always a fraction in this problem. There's always a numerator of 5 in this problem. I always see two numbers being added in the denominator in this problem, the first of which is the number 1. But after that, things are a little bit different, because if you look a little bit more intently at the second term in the bottom, it seems to change from 1 to 2 to 3 all the way up to 15. So what better example of a value that we might want to give a variable name, and you can use any variable you want. I like to use I as my counter because it stands for index. A lot of times you'll see K and J, and we know that this I is going to start at 1 and it's going to end ultimately at 15. And there you go. That would be your summation expression. Note the directions do not say anything about evaluating it or finding its answer. This one would be pretty tough to do. If you didn't have a calculator, your only choice would be to plug in the numbers 1 through 15 and add them manually. And the reason is because we don't have a special formula that lists I in a denominator's position. So we're kind of stuck. If we look at part B to finish things up, your answer is going to obviously have a summation notation in it. We know that. And then you see, okay, here's a term, here's a term, here's a third term, and then we have our nth term down here. What do we notice that's in common? Let's talk about this very superficially. In other words, I see a big old thing with the brackets around it, followed by a slightly smaller thing with parentheses around it for each term. There's nothing wrong with starting with that. I notice that within the brackets, it seems like 1 minus kind of leads things off. And then we have a parenthesis value that's squared. Okay, well, let's take a look a little bit closely at the parenthesis value. We see 2 over n minus 1 here, but then it moves to 4 over n minus 1 to 6 over n minus 1. So it's very clear that the value that I'm highlighting seems to be the part that's not constant. Everything else is constant. So I could put over n, and I could put minus 1 and be safe. And I could put 2 divided by n here at the end and be safe. But what I'm not safe with just this yet is how to write this numerator of this fraction. So 2, 4, 6 is an even series of numbers. If I use I as my counter and I want to start I at 1, then it just seems reasonable that I would put a 2 times I right there. Because if I is 1, you get a 2 up there. If I is 2, you get a 4. If I is 3, you get your 6. And you do that until you get to this value, 2 times n. That means you're going to put an n up there. So this one's not quite as cut and dry as part A because it has a more sort of secretive ending to it. But this is going to set the stage. This is not one of those things that we just kind of brush under the rug and we don't talk about anymore. This kind of summation is really what's going to drive the rest of topic 6.3. So we want to get you comfortable with them. This is the kind of topic that you don't want to just kind of wait and do the homework until after the entire lesson is presented. You want to start doing the homework problems in the skill builder just little by little so that you can keep pace with the content that's being discussed. And that's going to help you understand those really hard problems at the end. Anyway, I hope this helps. We'll see you next time.